Welcome back. In this session, we will see how to model a coolant temperature measurement. We all know in automotive engineering, the coolant temperature has to be measured properly in order for the engine control management systems, etc., have to work in a proper manner. So, there will be always an inertia between the application of temperature and the measurement time. Measurement by the sensor. So there will always be the delay. So how do we model that? That's what is the objective of this thing. And we will exemplify that through a temperature sensor example. So here you have got some fluid flowing through the system. And the thermometer is measuring the temperature of that fluid. So this can be exemplified like as a box diagram. We can consider this as some kind of a thermometer or an RTD. Or any thermistor or so, and there is a liquid which is at a temperature T, and the thermometer which is at temperature T. Our objective is to ensure that the thermometer starts measuring TL, but there will always be the delay because of the resistance and the capacitance that we had seen it in the earlier video, and this is where we will now invoke these two equations to find out how the dynamics works here. Okay. Now let's consider that we have studied that there are two aspects to the thermal measurement. One is the resistance and the other one is the capacitance. So what we'll do is we'll take the resistance part. How will we model a resistance of this particular thermometer? The whole idea is that the heat has to move from TL to T. I am assuming that TL is greater than T, the liquid temperature being higher than the sensor itself. So therefore, Q should be equal to TL minus T divided by the resistance R, which is in the path. So that's our first equation that we can conceive. Now, if you look at this system, intuitively it says to us that when heat is going to a thermometer will try to store the energy for some time, isn't it? So that particular thing that we can model it as Q1 minus Q2, whatever the heat which is going into the system, that should be equal to the thermometer's temperature change with respect to the time. Now in this case, there is no heat given up by the thermometer out. So therefore we can consider this Q2 as 0 and the Q1 can be taken as Q. So Q should be equal to C dt by dt. Now if we combine these two equations, 1 and 2, we get an equation like this, C dt by dt equal to TL minus T divided by R. That's our equation. And if I go ahead and put this in a proper way, C dt by dt equal to TL minus T divided by R. What is our objective? Our objective is to find out how the temperature of the sensor varies with respect to the time. We can take this equation as T should be equal to TL should be equal to T plus RC dt by dt. So this is a very familiar equation that you might have seen it even in our resistance capacitance model also. So this particular expression tells us that how the temperature of the sensor indicated with respect to time when it is subjected to a liquid at a particular specific temperature. That's what this equation is trying to tell us. And this is again a famous first order differential equation, and it's very similar to the RC circuit that we had seen it earlier. So when we solve this, we get a complete relationship between TL and T. So in this particular video, we had seen how to model thermal system with an example of a temperature sensor, and we will see you in the future videos. Thank you.